Hey class, this is our presentation about optimization. A few use cases for optimization are topographical maps, profit maximization, and volume maximization of a box. We have 3 steps for optimization. The first being finding the critical points by setting the partial derivatives equal to 0. Second step is to analyze points using the second derivative test. And the third and final step is to check the boundaries of the shape. So the first step for optimization is finding the critical points, which are points when the partial derivative of x and y are both equal to 0. And at these points, you're generally going to have local maxes and mins. For example, you're going to have valleys or peaks. But you might also have critical points that are saddles, which are critical points that are neither maxes or mins.
Okay, so the second step is the second derivative test, and so basically it's this. So d equals fxx at the point x0, y0 times fyy at the same point minus fxy at that point squared. And so x0, y0 is a point where just the gradient of that point is equal to 0, so just flat. And so what you want to do here is you get the answer, and if d is greater than 0 and fxx at the point is greater than 0, then f is going to have a local minimum at that point. If d is greater than 0 and fxx at that point is less than 0, then f is going to have a local max. And then if d is less than 0, f is going to have a saddle point, which is what we just talked about. If d equals 0, that's a special case. F can have anything. It tells you nothing, basically.
All right, now that you know what your function looks like at these critical points, you have to check if there's any critical points on the boundary of the region. And basically to do this, if we have this box right here with those bounds, you have to treat each edge like it's a single variable function, and you do that by setting the other variables equal to just a constant. So like for this bottom line right here, it would be y is equal to -1, and then x is just a variable. And then you take the derivative and you find critical points along that edge by finding where it's equal to 0. And then you just evaluate f at these critical points. And if that value is greater than any max or less than any min that you found in step 2, it's your new maximum or minimum. And depending on the situation, that would also be your optimal value. And then basically you just have to repeat that step for each edge. So for this box again, it would have to be 6 times.